Hello, we will now discuss about the RC series circuit with oscillating electromotive force. So this figure shows a series RC circuit with an impressed oscillating voltage E0 cos omega t. During the positive half cycles of the AC, the top plate of the capacitor becomes positive and the bottom plate becomes negative. Let us assume that the charge stored in the capacitor plate is Q. The direction of the current is shown in the figure, and we will take this direction as the direction of the positive current in the circuit. When we apply a voltage, there will be a finite potential drop across the capacitor and across the resistor. The potential drop across the capacitor is given by Q over C, and that across the resistor is given by R times I. So the applied voltage is E0 cos omega t, and that causes a potential drop of negative Q over C across the capacitor and Ri across the resistor. Let us take the steady state solution of the current as It equal to I0 cos omega t plus phi, where phi is the assumed phase angle between the input voltage and current. We know that current I is nothing but minus of dq divided by dt. Therefore, the charge q equal to negative of integral I dt, and that is equal to negative of I0 over omega sin omega t plus phi. Notice that in performing the integral I dt and finding out the value of q, that is the charge across the capacitor plates, we have not added the integration constant. This is because as the polarity of the AC signal changes, so does the charge distribution across the capacitor plates. That is, for an instant, let us assume that the polarity of AC is like this, plus and minus. So in this case, the upper plate of the capacitor becomes positive and the lower plate becomes negative. Now, as the polarity of AC changes, that means that when this becomes negative and this becomes positive, the charge across the capacitor plate also changes. So this becomes negative and this becomes positive. So we see that the charge distribution across the capacitor plates follows the oscillations of the applied voltage. Therefore, it is not necessary to add a constant of integration in equation number 3. We will now substitute q back into equation number 1, resulting in I0 over omega c, then sine of omega t plus phi plus r I0 cos omega t plus phi, and this is equal to E0 cos omega t. As we have done in the previous analysis, we have to expand sine omega t plus phi and cos omega t plus phi, and that will give us I0 by omega c, then sine of omega t multiplied by cos of phi plus sine phi, then cos of omega t. That is the first term, and the second term is plus r I0 cos of omega t, then cos of phi minus sine of omega t multiplied by sine of phi, and this is equal to E0 cos omega t. In the next step, we have to rearrange the terms in the left hand side of the equation in terms of sine omega t and cos omega t, and then we'll set the coefficients of sine omega t and cos omega t separately equal to 0. and that will give us I0 over omega c cos phi minus r I0 sin phi equal to 0, and the second equation is I0 over omega c sin phi plus r I0 cos phi equal to E0. From equation 4, we can write 1 over omega c cos phi equal to r sin phi, that is tan phi equal to 1 over r omega c, and we see that phi is a positive quantity, tan inverse 1 over r omega c. We'll now turn our attention into equation number 5 and write I0 as equal to E0 over 1 over omega c sin phi plus r cos phi. And this is equal to E0 over r cos phi 1 by r omega c multiplied by tan phi plus 1. And this is equal to E0 over r cos phi multiplied by 1 over r square omega square c square plus 1. We now have to find out an expression for cos phi. So the process for finding out cos phi is the same as that we have done for a RL circuit. In this case, we will multiply and divide equation number 6 by the square root of the sum of the squares of the coefficients of sin phi and cos phi in equation number 4. When we perform that, we'll get tan phi as equal to sin phi over cos phi and that is equal to 1 over square root of r square plus 1 over c omega the whole square divided by r omega c divided by square root of r square plus 1 over c omega the whole square. From where we'll get cos phi as equal to r omega c divided by square root of r square plus 1 by c omega the whole square. Now we have to substitute this cos phi into the expression for I0. That is I0 equal to E0 divided by r multiplied by r omega c divided by square root of r square plus 1 by c omega the whole square multiplied by r square divided by r square plus 1 by c omega the whole square, and this is equal to E0 multiplied by square root of r square plus 1 by c omega the whole square divided by square root of r square plus 1 by c omega the whole square, the entire square, and in this case this term and this term gets cancelled, resulting in I0 as equal to E0 divided by square root of R square plus 1 by C omega the whole square. Now the instantaneous current in the circuit is given by IT, this is equal to I0 cos omega t plus phi, and we have found out I0 and phi, and therefore IT, the instantaneous current in the circuit, is given by E0 divided by square root of R square plus 1 by C omega the whole square, then cos of omega t plus phi is tan inverse 1 by R omega c. So this is the expression for the instantaneous current in the circuit. If you remember, the voltage that we applied is E0 cos omega t. And the presence of the capacitor in the circuit introduces a positive phase, that is phi is positive in the RC circuit. That is, when we apply a sinusoidal voltage to a series RC circuit, the current leads the applied voltage by a factor of phi. Let us now see how this can be graphically represented. So we have represent the input voltage, that is E equal to E0 cos omega t. The peak of the input voltage is over here, and the waveform shown in broken line, that is this waveform, represents the instantaneous current in the circuit. We see that the peak of the current waveform occurs much before than the peak of the voltage waveform, and this is the phase difference phi, which is equal to tan inverse 1 by R omega c. As the peak of the current oscillation occurs a little bit earlier than the voltage oscillation, we can say that the current in the RC series circuit leads the voltage by a factor of phi.